this is Raj Patel, and today we are going to continue talking a little bit about dynamics, but instead of talking about centripetal acceleration, mostly, we're going to introduce Newton's law of gravity and hello, this is Raj Patel here, and today we're going to be continuing talking about dynamics, and now we are going to introduce something new, and that is Newton's law of gravity, and we are going to use it and tie it in with what we've learned about centripetal acceleration and other Newton's laws of motion. So, Newton's law of gravity first is this formula. The force of gravity equals big G, or the big G times m1, m2 over r squared, which is the distance between. And so m1 and m2 are just the masses of the two objects, and remember, gravity is all about the attraction between two masses, and if something has a mass, it has gravity. Even though it might be a small amount, everything has gravity as long as it has mass. And so, in this formula, m1 and m2 just represent the masses, and m1 is usually the larger mass, or the mass of the planet, and m2 is the mass of like the smaller object on the planet. And then, as I said, r is the distance between, and big G is the gravitational constant of the universe, which is 6.67 times 10 to the negative 11th, and the units are meter cubed per kilogram per second squared. So the negative exponent just means they're in the denominator, and the power is still the same. But this is just written in scientific notation. So scientific notation is just a way to abbreviate very small or very large numbers. And so let's do a simple problem using this formula. So what is the force of gravity between a 10 kilogram weight and a 100 kilogram person 2 meters away? So you do the same thing, you just plug in everything, and so force equals big G, so 6.67 times 10 to the negative 11th, and then the big M is 100 kilograms, the smaller one is 10, and the distance between is 2 meters. So you just plug in that, and you get a force. And be sure always to write your units. So force is always in newtons. And by the way, this is a very, very small force. So this is 1.667 times 10 to the negative 8th. So if you wanted the number in standard form, you'd move this decimal 8 places to the left. So it would be practically 0.000 newtons. So 0 newtons. So this force is very small between these two objects. And the closer the objects are, the greater the gravitational force is. And also, if you increase the masses, that also increases the gravity. So planets have such large masses that they actually have a significant amount of force. But next to you comparing to another object that is like a meter or so away, you barely have any force in comparison to planet Earth or any other planet you would be on, or any other larger object. So, applications of Newton's law of gravity. So Newton's law of gravity, first of all, can be used to find the acceleration on a planet. So, for example, we're gonna first derive it for you so you understand how it's calculated. So we have Newton's second law right here: force equals mass times acceleration, or the net force. And so remember back when we were doing free body diagrams earlier, the force weight, or you know weight is just mass times gravity. So this looks just like the summation of forces equals mass times acceleration. Mass, gravity is the acceleration. So think about this, and instead of weight just being mg, use substitute for Newton's law of gravity. So big G m times m over r squared equals mass times gravity. And so all we do is just cancel out these two little m's here, and therefore you get gm over r squared equals the force of gravity. And it's important that you see here that gravity does it, the force of gravity on something, on a planet, it is not affected by the mass of the smaller object. It's only affected by the mass of the planet. So when you're on planet Earth, it's pulling you with the same force as it's pulling the computer, or the door, or the house. Everything's being pulled or accelerated with the um, same force. So that's important because this also demonstrates that things fall at the same rate, with the exception of air resistance. If there's no air resistance, things will all fall at the same rate. So that's why in kinematics, we don't care whether it's moving up or down or horizontally, because regardless of where it is, it's always going to be pulled the same rate. And also, if you drop like a bowling ball and a feather, theoretically, a bowling ball or a tennis ball, both of them should fall at the same rate, because Newton's law of gravity here and this derivation shows that the mass of the object does not matter. So let's solve for the gravity of planet Earth. So what is the radius of the Earth if the mass is 5.98 times 10 to the 24th kilograms? And so this is the actual real mass of planet Earth, and we're gonna find out what the radius is based off of what we know. So here we have our general form: gravity equals big G m over r squared, and we want to find the radius. So we want to solve for r. So we switch g and r squared, with each other by multiplying each side by r squared and dividing each side by gravity. So we get this form, and then we just take a square root, and so you get this formula here. So now we plug in everything we know. So when you're putting in the calculator, it's always important to put scientific notation in parentheses. And I'm missing this parentheses here, but there should be a parentheses right here. And notice how 5.98 times 10 to the 24th, it's all in parentheses. Otherwise, it will really mess up your calculations, because the calculator would think that you're multiplying separate numbers, but you're not. It's scientific notation. So I would first multiply the top two numbers in scientific notation, then divide by 9.81, and I decided to use that because it's more precise than just calling it 10, the acceleration of gravity. And then we just take a huge square root of whatever this all equals, and you should get an answer of 6.38 times 10 to the 6 meters. And this is the real radius of the Earth. So the good thing is this problem's correct, and this formula works. And I did it myself, so I know that it actually does work out. But you just have to round the to 6.38. So, moving on. Here's a more difficult problem, but the same principle. If a planet with the unknown gravity has 9 times the mass of Earth, but has twice the radius, what is the gravity of the other planet? And the great thing about this problem is you do not need to know any information about the radius of the Earth, the mass of the Earth. You just use a comparison. So we're going to solve this problem just by using this equation and our math comparison skills. So we start out with our equation here. So big G, big M over R squared. So for Earth, let's call the radius and mass 1. So gravity, uh, so so technically gravity equals 1 because 1 over 1 squared is just 1. And the big G does not matter because it's a constant, so it's always going to be there. It does not affect the numbers of the problem. So we're going to call Earth, we're going to make everything number 1, so it's simple. And we're going to find out what G is. And if you put 1 over 1 squared, G becomes 1. So now we plug in what we know. So we multiplied the mass times 9. So instead of putting 1 at the top, we're going to put a 9. And then now we need the new radius, and so the new radius is 2. So we're going to put a 2 for R. So if we put in that, 9 at the top, and then 2 squared at the bottom, so we get 9 over 4, or 2.25. So if we compare the gravity of the new planet with Earth, so it's 1 to 2.25. So this means that the planet has a gravity of 2.25 times as Earth because we called Earth's gravity 1, and so 1 into anything is just itself, is just the number self. So if we divided 2.25 by 1, we would just get 2.25. So it is 2.25 times the gravity of Earth. So if you know the gravity of Earth, you found out the gravity of this planet. So I'm gonna simplify the gravity of Earth as 10. So the gravity of Earth times 2.25 equals 2.5 meters per second squared. And so that is the gravity of the new planet. And so this is kind of the style the AP physics or AP problems would be like, especially if you're taking AP Physics 1. I can almost guarantee you a problem that will be like this difficulty. So be sure to know how to apply your formulas and use like number comparisons. So now that we know gravity changes with the distance, why do we call G constant in kinematics if gravity changes? So let's imagine that we're dropping a ball off a 499 cliff and meter cliff, sorry. And so let's just say we're dropping off a ball. It's almost 5 kilometers, so still pretty far out. And so technically, the distance between the ball and the center of the Earth is the radius of the Earth plus the distance the ball is above the Earth. So, our formula for Newton's gravity has the distance between the two objects. And so, if we are above the Earth, we have to include the radius of the Earth because we always measure it from the center of mass of the two objects. So we have to count the center of the Earth to the center of the ball. And so the radius is technically the radius of the Earth, which is right here, plus the 400 4,999 meters. And so if we add that together, we would get 6,384,999. And so in physics, notice that usually we only write three significant number of figures. And significant figures are any real numbers, basically, and captured zeros. So to have three significant figures, we would just round the 8 up or down depending on what this number here is. And since it's a 4, we just keep it the same. And so we would just round to 6,380,000 meters instead of bothering to round it up. So since we're within three significant figures and we have the same numbers as the radius of the Earth, therefore, if we calculate it using this radius, we will always get 9.81 meters per second. And even if it was uh, exactly 5 kilometers above the Earth, it would only change by about a hundredth. So it would be 9.8 instead of 9.81. So even though it even though if we went 1 meter out it would change, it's such a small difference that we just call it constant. So we just keep it constant for all of our problems in kinematics. So this is why we don't even bother to care if it changes as it's moving. So now we're going to talk about escape velocity, and I do not know how necessary or how important this is to your class, but this is a kind of cool application of Newton's law of gravity, and so I just wanted to show this to you and share it. So let's talk about the velocity needed to escape in orbit. So escape velocity is the velocity needed if you're trying to leave a planet. So we have this is gravitational potential energy. This is from the energy unit, which was quite a while ago. And so remember, energy is just mass, gravity, and height. So now that we know that gravity changes with height, we just write mgm over r squared because that's the force of gravity. Remember, we canceled out the little m's because we know acceleration is only affected by the distance and the mass of the planet. And then r is just the distance between the two objects, and that would represent the height. So this is our new form, and then if we clean it up a little bit, we would get this. Negative gmm g big M little m over r. One of the r's cancels because the r squared is in the denominator and r is on the top. And then we just put everything together and we put a negative sign because the negative signifies that's being trapped by gravity. So because when you're in gravity, you are technically like stuck on the planet. You can't escape. So we're going to call that negative. And so this is why, because think of gravity as like you're in a bowl. So because you're in a bowl, you can't get out. So you're stuck in this location. So this planet here is orbiting around the Earth, and imagine the Earth in the center. And since it's in a hole, it will always keep on orbiting, because it will never leave because it's trapped. So that to escape, you just need the energy to equal 0. So 0 joules. So if we want this planet to get out of this bowl here, we want it to be at the top here where the energy is 0, and then it'll fall out or it'll just float away. So to get the energy to 0, remember we have potential and kinetic energy, and we do not have springs in, in space. So this so this is our formula here. So the gravitational potential energy plus the kinetic energy equals 0. And so we write our forms. So negative um, big G, big M over R, because that's the gravitational potential, plus the kinetic energy, which is 1 half mv squared, equals 0. And we cancel out the little m's because they're in all the terms except the 0, obviously. And so we cancel out the little m's, and this is what we get. So now we want to solve for velocity. So we move everything to the other side. So first we move this little part by adding it. So we add it to the other side. Then we multiply by 2, like this. And then because it's v squared, we just take a square root. So this is our formula for escape velocity. So let's calculate the escape velocity for Earth if we're 90 kilometers above the Earth. And so what is the escape velocity if the radius is 6,470,000 meters above, or away from the center of the Earth, and the mass, there should be another S here, sorry about that, is 5.98 times 10 to the 24th kilograms. So that's the mass of the Earth. And so if we plug that in, so remember, put scientific notation parentheses, and just do the square root, do everything as it said, and then just take the square root, and then you should get an answer of 7,852 meters per second, and that is really fast. So you really need to move very, very, very fast to escape planet Earth, or pretty much any planet. Even to escape the moon, you need like 2,000, about 2,000 or 3,000 meters per second. So that is very, very fast. So last thing I want to talk about is orbital velocity. Again, I don't know how useful this will be, but it's a cool application of Newton's law of gravity. So we start out the same. Net force equals mass times acceleration, Newton's second law. And instead of we just cancel out the little m's, because if we put in Newton's law of gravity here, the little m would cancel out with this. And instead of acceleration, we put centripetal acceleration. So from the last video, this is where we involve centripetal acceleration. And so because it's moving in a circle, so whenever you're in orbit, you're just moving around the planet, so you're always turning and accelerating centripetally. So if we want to get the v isolated, we move r to the other side, multiply each side by r, so one of the r's cancels, and then we take a square root. So we get this formula. So square root of gm over r. So this is orbital velocity. And so this basically just says that as the mass of the planet gets greater, so does the orbital velocity. And as we go farther and farther out, we slow down. So that's what the formula means, because r is at the bottom. So if we increase r, orbital velocity decreases. If we increase the mass, the orbital velocity increases because it's in the numerator. So if we do this, let's solve a problem with this. So let's just say you want to escape from an orbit. So we're going to combine orbital velocity and escape velocity. And so we're in orbit, and now we want to escape. So we want to figure out the velocity we have to add to escape. So the escape velocity is higher than the orbital velocity. So if we figure out the difference, we can figure out how fast we have to get to actually escape. So here is our formula. So we have the escape velocity from the last slide is the square root of 2 gm over r, and then the orbital velocity is just square root of gm over r. And so notice how they're very, very similar. So it's just a slight difference. So we want to factor out this term, the square root of gm over r. And if we do this, this one has a 2, and then this one just has a 1. So we get a square root of 2 minus 1, and then we keep the subtraction sign. So this is the difference between the velocities here. And so if you actually do this in your calculator, square root of 2 is about 1.41. And so if you subtract that from 1, you get a 0.41 of the orbital velocity. So basically, you have to increase 0.41 of the escape velocity, or that's how much you have to increase to escape in orbit. So this is a cool thing if you're into space and satellites, and so this is how fast you have to increase your speed to actually escape in orbit. So thank you for watching Mirage's physics video. So today we talked about Newton's law of gravity, and we introduced it and sort of tied it in a little bit with dynamics and centripetal acceleration. So tune into the next video to learn about rotational motion. So we'll talk about torque and rotational kinematics, and we'll talk about how to convert between rotational and linear motion. So if you liked today's video or enjoyed it, please like the video down below and spread the word. And also email me any questions you have. I'm happy to answer any problems you have at mpatelbuccaneer@gmail.com. And please practice what you've learned, and if you keep on practicing, I'm sure you'll remember it and ace the test. And so for chemistry tutorials, if you're taking chemistry, please visit my website, buccaneerchemistry.weebly.com. And thank you for watching, and I hope to see you next time.